Okay. Okay. I guess we can start. Let's see. I want to start chapter 6 today, which is continuous time Markov chains. And I have two examples, but I guess I'm going to kind of go on a rant before I go into these examples. One example has a salesman who's flying from Atlanta to Boston to Chicago and back and forth, and you want to know, as usual, why would you want to know? But anyway, you want to know what fraction of time he spends in each place and how many trips a year he makes from Atlanta to Boston and so forth. Okay, that's problem one. And then problem two, which is very typical, is you have a couple of machines and they occasionally break down, and so the machines are operating for a random period of time and they break down at some sort of constant rate, maybe different for the two machines, and there's a single repairman. So when the machine breaks down, then the repairman starts to work on it and repairs it, also we assume at a kind of constant rate, a tendency to repair. And you could have both machines down. The repairman has to pick one of the machines, so you have different policies. One policy would be that the repairman works on the first machine to break down and keeps working on it until it's fixed. Another policy would be that one of the machines is much more important than the other, so when the important machine is down, he always works on that one. So if he's working on the less important one first, he switches to the important one. But you can only work on one machine at a time. Since there's two machines, you might have them both down. So they could be all up or all down, and then there's different rates for the failures for the two machines, and there's different rates for the repair by the repairman. And that's continuous time Markov chain. So all this is supposed to be in continuous time. And going on the trips from Atlanta to Boston to Chicago is the amount of time he spends there is continuous. We're not doing things in discrete time. So it's continuous time. But I first want to give a kind of overview. This is, and I guess as usual, there is notes, so you don't really need to take any notes. I mean, you can if you want, of course. That may keep you awake, but there'll be notes online, so you may find the notes online written a whole lot clearer than what you're hearing. But anyway, that way, I mean, the point is, I think a reasonable strategy, which many of you have adopted, is not to bother to write down notes, just listen and try to absorb things in real time, and then you'll see enough there in the notes that I think that's effective. Okay, well, I want to now, this should be clear to you. I want to characterize, as I've done this, I guess almost every other class or every class, or maybe 5 times during each class, I characterize how you analyze discrete time Markov chains. And I want to review that, and this is sort of like, what's this all about? So you make a model. And in discrete time Markov chain, that model is the transition matrix P. And you solve the model. And well, if we think of the characteristic case, so think of irreducible and positive recurrent, which is finite, if it was finite, for example. Think of this case. So that's kind of the main case. There's all that other complexity about canonical forms and absorbing, and there's a bunch. But there are not too many cases. But this is the main case. So solving, you do pi equals pi p. And there may be shortcuts, right? Like in the exam with the moving around on the graph with the weights. There's shortcuts to solve this, but it's fundamentally you're solving pi equals pi p. So the point is, when you make the model, you make P, and when you solve it, you solve pi equals pi P. That's sort of the whole, mostly the thing. Well, there's a couple of other variations, but that's the whole story. So continuous time Markov chains, I guess the main point I want to make is the story is actually different, quite different. But the fundamental idea is very similar. The idea is you make a model in a simple way, and you solve it in a simple way. And indeed, the standard form is the model's a matrix, and the solution's a system of linear equations, just like this. But it's not so obvious what it is. Now, the obvious thing that you would think of is that there would be a continuous time transition matrix. I mean, instead of here, there's actually a process. So lurking here, which we don't need to talk about too much, is this process, which, or n greater than or equal to 0, xn would be the state of the Markov chain in state. But in some sense, you could talk about this process, xn is the state of the Markov chain that goes with pi and p. Okay. Here, if there was a process, it would be x of t, t greater than or equal to 0, which is in continuous time. We now want it to be continuous time, not discrete time. So if you had a continuous time process, you would want to have something like this. This is the transition probability in t, so you'd say you'd have this continuous time process, and here's time s, and here's time t, s plus t, right? So this is t units later, and the probability of going from I to j would be pij, but t. It would depend on t. Before, this would have been a 1 here. So there would be a transition matrix. So when we deal with continuous time Markov chains, the process will be continuous time, x of t instead of xn, and there will indeed be a transition matrix, p of t, instead of just p, as a function of t. But this kind of is in the background. That conceptually, this is here. This is the idea, that this process is a continuous time Markov chain. So for any s and t and I and j, you have this relationship. That would be saying we're assuming this process is a Markov property, and if I condition on the past here, if I put stuff about u before s, anything I stick in, that's the Markov property. If I stick in extra history before s, it's not going to change anything. That's the Markov property. So you might think, and it's true, that this is the Markov chain that you look at time 1. This will be a transition, and this, for each t, the matrix here, will be a transition matrix for a discrete time chain. And in particular, p of 1 will be 1. So you could think, oh, I'll just look at the thing in steps of 1 and so forth. And these would be all discrete transition matrices for discrete time chains. Well, conceptually, this is saying, oh, if I've got some process x of t, and I'm going to assume it's Markov, I'm going to have this property where if I put history in here, it's not going to make any difference. That's what I mean by the Markov property, and it's continuous time. So for any s and any history before s, the probability of going from I to j in times t is going to be this. Okay, that's sort of what I want to emphasize is that's conceptually, and it looks like it fits here. Instead of this p, you have p of t. Right? I mean, that's sort of one way of looking at this. The problem is that you don't know how to specify this. This is the problem. In other words, this thing is not one function. This is a single matrix. This is a matrix for every t, and we don't know how to define it. So this is not the model specification. The point is this conceptually is there, but we can't start there. That's the problem, that we don't work with this. So therefore, this model, we're going to put a model, and we're going to solve, but it's not going to be p of t. So you want to think about it differently. The p of t exists. I mean, there'll be some math that says under certain conditions when you introduce the model p of t exists, where p of t refers to the matrix that's pij of t, I ranging through the states and j ranging through the states. So for each fixed t, it's a matrix. This is a matrix for each fixed t. And you could think of that, and it has the properties of a transition matrix. Okay, let's see. So the problem then is, how would we specify the model and how would we solve it? And I'm thinking we're in this case, when we shift here to continuous time Markov chains, we're almost always in this domain where we no longer care about absorbing and all that. We're always solving irreducible and positive recurrent. That's sort of almost the whole thing. You want to know this long-run steady-state behavior. But the problem is not so much finding the long-run steady-state behavior as specifying the model. What do you mean by the model? It's going to go in continuous time. So with this, let me start with one. So the model, let me just try to outline. The model, there's two views. The rate view and the semi-Markov process view, which is really in Chapter 7. This will actually be discussed in Chapter 7, not here. But it is easy to understand, so we'll start here. So let's start with the rate view. And this starts with a little theory, in a sense, because we start with this, but we don't know what it is yet. This is conceptually. We're going to have this Markov process. It's going to have a transition matrix. Let's just think about how that evolves, that transition matrix, and we'll see that we'll end up with something simpler. So when you do these, when in the discrete time Markov chain, you would have said p to the n plus m is p to the n, p to the m, right? The n plus m step transition matrix is the product of the n step of the m step. This is the Chapman-Kolmogorov equations. For continuous time, there's an obvious analog. As matrices, not numbers, matrices. This is saying the transition matrix in t plus s steps is the transition matrix in t steps times s steps. First you do t steps, then you do s steps. So you're saying pij in t plus s is equal to, if you just write this out, this is pikt pkjs, sum on k. So you say, well, I'm going to go from I to j in times t plus s. I'll go from I to k in time t, and then from k to j in type s, and I sum over all possible k. This thing is exactly the same thing as this. It's just happening at times st and t plus s instead of discrete times. So this is the same Chapman-Kolmogorov equations in continuous time. So that's what you want to have happen. You're going through according to this Markov property, and it produces this matrix equation. Now you want to look at S as some h small, because we're going to do some calculus. We're going to do calculus here. So if I rewrite this, I've just relabeled S as h because h, like calculus, is the small number that's going to go to 0. And then I subtract p of t from both sides. Now, I subtract p of t from the left side straight away, right? No trick there. On the right-hand side, it's a little tricky because I've subtracted p of t, but p of t times the identity matrix is p of t. This is the identity matrix. So this right-hand side is, I've subtracted p of t, just like this, but then I've rewritten it this way. Because this is the thing I had before, and when I subtract p of t times I is p of t. So this is just the same thing as before. Now I divide by h. Okay? Now I let h go to 0. This is all matrices, but it's the same idea. This thing we've just produced is an ordinary differential equation. The derivatives, these elements here are dpij of t dt for each ij. So this is a matrix of derivatives and this matrix of derivatives. This thing is written down for matrices, but it's just a matrix for each ij component. It's just the derivative. Standard derivative for each element of the matrix. So I've got, this is a matrix equation, this is a matrix equation. I let h go to 0, I get the derivative here, and I get the derivative here. This is going to be, we're going to call this q. This is the derivative at 0. Once we stick this in here, we're going to have a differential equation. An ordinary differential, linear, first order, simple differential equation, except in matrices. So we've got, in this case, we've got here, we've got p prime of t equals p of t, q equals q p of t. Now I've written this, there's two equations. I could put it in either order, and that's because I could put this in either order here. Matrices don't commute, but in this case, I could put s and t, I could put them in either order. Just change the labels. So actually, I could change the order here because it's still true. Not true in general. Matrix is not true that AB equals BA for matrices, even if they're the same dimension. Right? In general, this is not true. Not always true, but it is true here. And therefore, I could have put this on either side, and therefore I could get either this or this. So, when I write this down, there is this q, which is going to be the data. And that's exactly what's going to go here. The data is going to be q. Given q, given this q, p of t itself solves an ordinary differential equation. So then automatically, this implies p of t equals e to the qt. This is the matrix solution of that. Yeah?
How do you make derivative of p of t equal to p of t into q?
So this is the derivative of p of t when I let h go to 0. This is the derivative of p of 0 when I let h go to 0. Here we are, and q is by definition this derivative at 0. And I could do it in either order. Because here, I can write this in either order because this is going from, I can go to t and then s, or I can go from s to t. Because of the special structure of this problem, I can either say, well, let's go t forward and then s after that, or s first and then t after. Same, it's true especially here, not in general. So this equation, this can be in either order. And I could have switched the roles here. Because that's just changing, all I do is change the meaning of t and s. T and s are arbitrary, so just change the meaning. You know, call st and ts. Because it's true for all s and t. So, but it's special here. The order is special. And so you produce this differential equation. And this is just like in a deterministic, the most elementary linear system. It's saying this system behaves according to an ordinary differential equation. When you have an ordinary differential equation like that, all you have to do is specify the initial point, the q. So if you specify the q, if you know q, then p of t follows, and it turns out this, just like this is the obvious generalization as if it was one-dimensional. This would be the answer if it was one-dimensional. Right? I mean, it's just an ordinary differential equation. So, indeed, this is probably somewhere in your calculus history. This is not requiring that you have a course in differential equations. This is the simplest differential equation, which is usually in one of your high school calculus courses. Okay, so it's there. This stuff is there, but the matrix version won't be there, but everything generalizes. So, but it's good to review ordinary differential equations, simple linear ones, if you're not familiar, because that's related to this. Now, that says the model's Q. So then what you want to think about what that's doing, this is saying this is saying that Q, so if you think of some element of this, this is the intensity, right? Qij is this derivative of the matrix. So it's the intensity at a zero time, in a small, at any given time, Qij is the rate or intensity of going from I to j. Given that you're in I, what's the intensity or rate of going to j? And you're saying, in this model, you're saying, oh, at any time, when I'm in state I, there's an intensity Qij of going from I to j. That's the model. That's the one way of viewing the model. The model is, it's all in continuous time, and whenever I'm in state I, for any I, there's an intensity to go to other states. Constant, no matter when the history or everything, Markov, doesn't depend on anything. When I'm in I, there's an intensity, Qij, that I'll next go to j in a small little interval of time. Defined precisely as the ordinary differential, as the derivative. But it's an intensity, so you're thinking, oh, when I make a model, I specify the intensity that things are going to happen. That's exactly what you do with the machines. When the machines break down, you say, oh, machine 1 has an it's going to break down at some rate. That's exactly, you're specifying the Q matrix. And when the repairman's working, he's repairing these things at a certain rate. I mean, it's going to be random, but there's a certain likelihood that it's going to intensity at which it's going to happen at any time. So the model becomes these rates in this view. In this view, you define the rate at which things, the changes of states might tend to occur, which means which means exactly this derivative. In other words, the implication is that Qij is equal to Pij derivative at 0, which is the derivative of the transition probability at 0. So this is, Pijt is the probability of going in a little from I to j in a small time t. This is the derivative. That's what it means. So there is this rate, which you should understand intuitively, but mathematically it's just the derivative of the transition function. The tricky part is that you don't know the transition function. You're going to define the model by specifying. You've elected. When you use this method, you're electing to define the model by specifying these rates. That may initially seem crazy and less obvious than the discrete time, because you're specifying infinitesimal rates, and it's kind of hard to convince yourself that that makes sense to do that. But the model is Q. The model is this Q. So when you make the model, you're going to think, here you say, oh, when I'm in I, what's the probability of going to j next? That's Pij. Here you're going to say, am I in I, what's the intensity or rate of going to j next? Okay? Okay, now let's think about how to solve it. And that's going to come out of this too. Okay, it's going to come out of this also. And let's take this. So we have this thing. Now, we're now thinking, what happens in the long run? Well, in the long run, well, let me write this. I'm going to write this differently. I'm going to use a different notation for the steady state distribution. So this is going to be saying, the point here is we're going to assume, as before, the nice case where the chain is irreducible and positive recurrent. So in that nice case, we're anticipating that Pij of t, the probability of going from I to j in time t, is going to go to some limit as t goes to infinity. Alpha j. We'll call it alpha j. That this is going to happen. That's sort of like intuitively, that's obviously what happens, and now it ought to be going nicely to here. And if you did it in matrix form, all the rows would be the same, because this doesn't depend on I. No matter where you start, there's going to be a limiting probability of being in each of the states. So Pij of t is going to go to alpha j for all I. just like before. And if you did it in matrix form, all the rows would be the same. That's saying the same thing. Now, look at this differential equation. What does that mean here? What ought to happen intuitively? This goes to the matrix of constants. What should happen to the derivative? If P of t goes to a constant, what happens to the derivative? 0, right? It doesn't have to happen, but obviously it will happen. What do I mean by that, right? So this equation goes to, if I write one row of this, this is now 1 by n and n by 1, and therefore this is 1 by 1. But I want to draw a picture. So this, we're saying Pij of t. So what typically happens is it looks like this, right? 1, 0, and something happens, right? Here you are, and here's t. And it looks something like this, and sure enough, it goes to a limit, and the derivative's going to 0, right? Okay, now what could happen? Well, in principle, this could happen, this could get smaller, but these things could get closer together, and yet all the time there are little wiggles, so the derivatives don't converge. I'm just saying, the fact that this converges to something doesn't imply that it's smooth, because it could be oscillating even smaller very fast. This could happen. Just to say, the fact that the function converges doesn't imply the derivative, because it's more delicate. Just to saying it, this would be bad. You know, in other words, it's getting close together, so it definitely converges, but the derivative, I'm just drawing a function that could be bad. This doesn't happen, right? It doesn't make sense it would happen, and it doesn't happen. I'm just showing mathematically the fact that this converges doesn't imply this goes to 0. But surely it will if everything's reasonable, and it is, okay? This is part of the math that you could do in the background. Okay, so all I'm saying is this should go to here, and so this will go to a constant, and this should go to 0, and all that happens. And that's the thing you want to know. So then you have this. The story is just like this, and yet totally different. The model is a matrix. The solution is a system of linear equations, but the matrix is totally different, and the system of equations is totally different. The matrix that you use, the model, is the derivative of the transition function, not the transition function itself. And the system of equations is this thing that comes out of the differential equation, which has got 0 here. And that's just this. This becomes 0, and this becomes alpha as t gets large. So that's just this, taking one row out of this. This should be this vector. This thing is a row vector probability, and this is an n by n matrix, and this is 1 by n, all zeros, right? So you've got a system of equations. Just like this. This is n equations. And Q is given, and these are the n unknowns. And before, you're going to have, as before, you're going to have the same kind of story that the sum of these probabilities is, but there's got to be 1. So actually, there's a redundancy here, just like before, and that there's n unknowns, which are the alphas, but they sum to 1. And you use that because they're probabilities. So these are probabilities, and that's what you want to find. So the model is here, and you want to find the alpha. The model is here, and you want to find the pi. Solve the system of linear equations. Just like before, there are shortcuts to getting the pi in many cases. Reversibility will be even more important in continuous time. Same story. So there's a very definite parallel, but the model is Q instead of P, and the system of equations is alpha Q equals 0 instead of pi equals pi P. But there's a definite direct parallel, which this is a slightly different cut. Ross will not put it this way, so this is to give a different cut on what's in the chapter 6. Okay. Now, actually, there's yet another view that's also useful. There's a different view. So that's the rate view, and by rate, I mean the Q matrix. The model's the Q matrix. Now there's this other view that's a semi-Markov process view. And this view is that you start with a discrete time Markov chain, and then you have holding times. So this is good from the example. Let's do the example. Let me talk about this example. Here's an example, and it's well illustrated by this example. It's continuous time, and yet it comes at you discrete time. So it's not going to be like this. It's going to have a different story. A salesman flies back and forth among the cities Atlanta, Boston, and Chicago. From Atlanta, the salesman goes next to Boston or Chicago with probability 1/2 each. From Boston, the salesman goes next to Atlanta with probability 3/4, and Chicago with probability 1/4. And from Chicago, the salesman always goes next to Atlanta. However, the salesman stays a random length of time in each city, exponentially distributed, with mean 1/4 month in Atlanta or Boston and 1/5 month in Chicago. So what you're told here is that you have a discrete time Markov chain. You're told where the salesman goes next from place to place. And then later on, you're told how long he spends at each place, which is not constant but random with a continuous thing. So actually, you're given a P and an M. And the P, so let's think of P. We have Atlanta, Boston, Chicago, Atlanta, Boston, Chicago. This is being specified. A discrete time Markov chain is being given. When I'm in Atlanta, I go next here. So what we're describing, the discrete time Markov chain, is not telling us what happens at real time. It's telling us what happens from transition to transition. When we're in Atlanta, this says we go next to Boston or Chicago with probability 1/2 each. Whenever we go. But when we leave Atlanta, we go next to one of these two places with these probabilities. And when we're in Boston, we go next to Atlanta with probability 3/4 and next to Chicago with probability 1/4. And when we're in Chicago, we always go to Atlanta. So here is this discrete time chain, given to you straight out as a discrete time chain. The model is being specified this way. There's no rate matrix. It's being specified. Here's a discrete time chain given to you. Now you're told that the mean time that you spend in each state, in Atlanta, a random time in each exponential 1/4 month. The mean time in Boston is 1/4 month. And the mean time in Chicago is 1/5 month. These are exponentially distributed. So if we think of the probability of the time spent in Atlanta greater than t is equal to e to the minus t over ma, right? This would be exponential. This would make this exponential, deducing the tail probably, right? So this would be 1/4 month. This would be the distribution of the time I spend in Atlanta each time. If I go to Atlanta, this will be the probability distribution of the time I spend in Atlanta, just exponential. So here, the story, the semi-Markov process is a variation of this where these times don't have to be exponential. They could be anything. There's some other distribution. And then the question is, the point is, well, this is a continuous time model. Here's the discrete time chain, and here are these random holding times. So the question is, how is this model related to this one? And how would you solve it? So it's perhaps easier to think of this as what conceptually would be the long-run fraction of time you spend in Atlanta. Okay, this is the thing you want. Just imagine this data and don't try to construct Q, just do this straight away. So the first thing is you want to know, the first thing is you could say, well, let's consider the fraction of transitions started in Atlanta. So if I do that, then I'm doing this discrete time chain, right? It's this discrete time chain. So if I do that first, I would find pi equals pi p. And I'd know that pi a is the fraction of transition starting in Atlanta or ending in Atlanta. Right? This would be the answer at transition epochs. But now I want to know the fraction of time that I spend in Atlanta. So that's going to be not pi, but this is going to be the alpha. So what I want to emphasize here is the intuition. I'm not really proving anything. I'm just emphasizing the intuition. So it ought to be clear to you what the answer is. I mean, how would you take the pi once you found it and convert it into the alpha? I mean, what the point is if you spend a long time in one of these cities, like if you spend, every time you're in Atlanta, you spend more time there than when you're in Chicago. So somehow the alpha sub a is going to be somehow bigger than the pi sub a, right? Because you spend more time there each visit. And the obvious answer is this. The obvious answer is the fraction of time spent in I is proportional to the fraction of transitions times the mean time. Okay, I'm contending this is the obvious answer here. And that's the general formula. So the thought is here, we've got a continuous time Markov chain, all right, but we've defined it in terms of the discrete time chain and the holding times. Defined differently. Different model. These two things are the model now. But in this model, we know how to solve this, so we solve pi equals pi p, and then we adjust the answer to find the alpha. So it's a totally different analysis, different representation of the model, right? The model is here with a discrete time chain plus these random holding times. So you have this alternative view. So when you do this, I guess this is solved in the example. So here's this, and here's all this stuff, and in the notes you'll see the solution for pi and the solution for alpha. Yeah.
Doesn't that also say that this model kind of is independent of how the time is distributed?
Yeah. So it turns out the semi-Markov says these times, the exponential part doesn't matter. And that should make sense to you because you think in the long run, you're going to visit this fraction of time and you're going to spend this fraction of time when you're there each time. And so the distribution is going to change the sample path, whether it's lots of short ones and long ones and so forth. But in the long run, you're going to, your fraction of time, you know, the average time you spend in A per visit is going to be that average, the mean of that distribution. So this shows that I haven't said that, but this formula is valid for arbitrary distributions as long as they have means. So it doesn't have to be exponential. And that's why it includes semi-Markov processes, because the times aren't exponential, the same answer. So that's why it's called the semi-Markov process view. But this is one way to look at a continuous time Markov chain. A continuous Markov chain is a discrete time chain at transition epochs, and then random times staying there. And then when you want the steady state distribution, you take the steady state distribution of the discrete time chain and weight it by the mean holding times. Should be totally intuitive. Oh, and the notes will be there. You haven't been through 6, but this notes will be there to parallel. I mean, what I'm saying now will be in the notes, and Ross will say something different, and hopefully over the next couple of weeks, all this will integrate in your mind. Okay? That's, I think, will be okay. Now, the obvious question here is, how is this related to this? So what we want is we want to say, well, if we model this way, I want to be able to construct this version. And if I start with Q, I want to be able to construct that. And that's actually not hard, right? So I actually made two models, see? These are two different ways to produce this model. In both cases, I'm getting formulas for alpha, right? But they're different formulas. So the point that you want to do is now we've got two versions of the model. The other version is P and M. So the issue is, how do you go from Q to P and M, and how do you go this way? Because there's two representations of this model. So here, let's think about that here. What should be Q, Atlanta, Boston? This is the rate of going from Atlanta to Boston at any time. So the way to think about it is, what's the rate at which I'm going to leave and go anywhere? Just leave. The rate at which I'm going to leave is the reciprocal of the mean. This is the rate I'm going to go somewhere, which I'm also calling, this is the rate this way. Given a notation for the intensity, which is just the reciprocal of the mean time. And this is this exponential. Given that this becomes important, that this TA is exponential. So actually, when I wrote it down, if I wrote it with a rate in an exponential, if I wrote this down, PTA less than or equal to t, say, is 1 minus e to the minus lambda a t. This lambda a would be exactly, or if I put nu a here, it would be this. So this exponential has a rate, and that rate is what's exactly going here, just like always. That the intensity of going from A to B is the intensity of leaving A times the probability of then going from A to B. This is the rate at which you leave A, and this is the probability that you go from A to B. So there's taking MP going to Q, just as you would expect. Now, if we go the other way, let's consider going the other way. We want PAB. We want to say, well, when we got this Q. Well, you want to know the probability of going from A to B. It's Q, the intensity of going from A to B, over the sum of the intensities of going from Q anywhere, right? Else. So this is the intensity of going everywhere you could go, and this is the intensity of going. And the point is, there's a ratio of intensities that's independent. It's happening all the time. These rates are constant. So the intensity of going from A to B and from A to C is constant all the time, and the probability of going from A to B is the ratio of the intensities, which is, again, the property of the exponential variables. But anyway, this is this. So if we wrote it if I wrote it in the general form, I would write this. Now, I'm excluding, this is the intensity of going from I to J, and this is the intensity of going from I anywhere. But I exclude I because I'm not going from I to itself. I just stay there. There's no, here you don't go from a state to itself because you're doing these transitions, so that's being excluded. You're not going from I to I. You just, if you don't go somewhere, you stay there. The intensity of leaving, then, the intensity of leaving is the intensity of leaving is just the sum of the intensities of going all the other places. And that's made by definition the negative, so QII by definition is minus the sum of these. So we put this on the diagonal. But at any rate, given Q, here's P and here's nu, which ought to make sense. In other words, the probability of going from I to J is just the intensity over the sum of the intensities. And the intensity of leaving I is just the sum of the intensities of all going wherever you can go. And of course, if you solve the equations both ways, you'll see that either way you write it, any one of these two methods is going to imply the other. So it gives you the same answer. Now, the point of these two examples, now we're floating along, I'm ranting and raving here. Maybe we have time for the other examples. The point of this point is, let me just kind of summarize what I've been trying to say. I've been trying to say for discrete time Markov chains, model is P, solution is pi equals pi p, at least in the irreducible positive recurrent case. In continuous time Markov chains, there's actually two models, with the semi-Markov process view and the rate view. The rate view says the model is Q. The semi-Markov process says the model is P and M. And you can go back and forth. And in one case, in this case, the alpha that you want is alpha Q equals 0. And here, the alpha is alpha j is the sum of pi j mj over the sum of the pi k mk's, right? So this model representation has a solution procedure. This model representation has a solution procedure, and you can go back and forth. Okay, now the two examples that are my intended discussion are each written so that they're in one of these two frameworks. In other words, the problem about the salesman going from Atlanta to Boston to Chicago back and forth was expressed directly in this terms. The data was given. You were given the data in the form of the discrete time Markov chain at transitions, and you're given in this case in the ABC salesman, you're directly given P and M. That's the data. Looks just like this, straight away. You're told from here, you go next to here with this probability. So the data is, you're actually made the model data. The model data is directly in the semi-Markov process form. So it's convenient to know that that's a natural way to directly look at it, rather than to think I have to convert it into the other form and so forth. This is one representation of the model. The other problem is put in the other model framework, and it'll look totally different. So part of the story is to recognize that there are essentially two ways to look at this, the semi-Markov process and the rate view, and usually the problems in front of you will be just one of those, straight away. Okay, so let's do the machine problem, which is is in this rate view. So here there are two machines, and let me say machine one, and well, let's see, two machines, and well, 1 and 2, and this could be working and then failed. Okay, so here's failed 1 and 2. So if machine 1 is working, there's an intensity lambda 1 of it breaking down. And if machine 2 is working, there's an intensity of breaking around lambda 2. Now, if the repairman's working on it, mu1, mu2, the mu's if working. So there's actually here only one repairman in two machines. So if both machines are working, they're each failing at this rate. Or if one's working, it's failing at that rate. If the repairman's working on the machine, if it's broken and he's working on it, it's being repaired this way. So the data is just these four rates, different for the machines. Now, the obvious thing you'd like to do is you might do something like x of t equals number of working machines. And you'd like this to be a continuous time Markov chain, so you'd have states 2, 1, 0. So let's think of it 0, 1, 2. This is common to draw a picture like this. At this point, if these two machines are working, they're both failing One's failing at rate lambda 1 and the other's failing at rate lambda 2. However, if you have, once you start having these other situations, it depends on which machine failed, right? If you try to work with this and you have these three states, you don't know how to go forward because it depends on which of the two machines is working at that time. Or if you're here, it depends on which machine failed first, because the basic rule is the repairman works on the machine that failed first. That's the first policy. We don't know that here. So we need a more complicated state space. So here's a more complicated state space. They're both working. This is 1 is working, 2 is working. Then down here, 0 working, but we should put 0 working, 1 working, so 2 failed first, so 0 working, 2 failed first. Let me put that here. 0 working, 1 failed first. Maybe my labels aren't too good. This is saying they're both working. This is 1 is working, 2 is working. Let me put this 0 working, but 2 failed first. 0 working, 1 failed first. Right? So 2. So now here, how do I get here? If only 1 is working, 2 is failed at this rate. 2 is both of them are working, but only 1 is working, so 2 fails. That's what I'm getting here. Over here, 1 fails. Now 1 is working, so the only way I can go down here is now 2 fails. And here, now 1 fails. So that's all the failures, right? I'm here. They're both working, so I could go this way. If 2 fails, I go here. If 1 fails, I go here. With 1 working, 1 working. Here, 2 is working. Right? Please complain. Were you going to complain? Good. I hope so. Somebody going to complain? If I write the wrong thing, I hope so. I hope this is making some sense as I'm going through this. Okay, both are working. Machine 1 fails at lambda 1. Machine 2 fails at lambda 2. If 2 fails, there'll be only 1 working. If 1 fails, only 2 will be working. With 1 is working, it can fail. If 2 is working, it can fail. This way. Now, whenever there's a failure, the repairman's going to start working. So if 2 is failed, the repairman is trying to repair 2, and it's going to occur at this rate. 2 is failed, the repairman starts to work on 2. 1 is failed, the repairman starts to work on 1. Now, here, 2 is failed, 2 failed first, so he's going to work on 2. Wait, if he's going to work on 2, and they're both failed, 2 is going to get fixed. He's going to work on 2. That's going to take him, 2 is going to be working. You have to be careful, right? That if they're both failed and 2 failed first, he's going to work on 2, and so he's going to come back here, 2 working if it fixed. That's what at that rate. And here, 1 failed first, and he's going to work on 1. Is that actually okay? So now you see there are 5 states, and in each state there are intensities or rates of going to the other states. Directly, the model is actually directly defined in this rate view. You're told that, whenever machine 1 is working, it's failing at rate lambda 1. Whenever machine 2 is working, it's failing at rate lambda 2. Whenever the repairman's working on machine 1, he's repairing it at rate mu 1. Whenever he works on machine 2, it's being repaired at rate mu 2. So what I just said implies this picture of rates, a rate diagram. And this is sort of the standard thing you'd write down if it's if the state space is 5 or 6 states or 10 states or something, you could draw a picture like this to construct. Then you would write down the Q matrix. So you have these states, 2, 1 working, 2 working, 0 working, 1 failed first, 0 working, 2 failed first. And just write those down. 2, 1 working, 2 working, 0 working, 1 failed first, 0 working, 2 failed first. Of course, you could call these states 1, 2, 3, 4, 5, or whatever you want, but that's what we mean. So then you think, well, what is the Q matrix? From 2, you go to here. You just read that off. You go lambda 2 here. 2 working is lambda 1. Those are the two ways that you can go out of 2. And then from 1 here, 1 working. So 2 could be fixed. 1 working. Now then also you could have 1 failing. So you go 1 failing, 2, 1 working, 2 failed first. 1 working, 2 failed first would be lambda 1 working. And lambda 1 would be here. And so you're entering this matrix. You're just taking these rates out of 2 are going to be the row starting from 2. Rates out of 1 are going to be the rates out of there, and so forth. You just fill this matrix in. You're not putting anything here or here. These diagonal entries are going to be the negative of the row sum. By definition, this is going to be minus lambda 1 plus lambda 2. This is going to be minus lambda 1 plus mu 2. And so forth. Yeah?
Why do you need a 2 there?
Pardon?
Why do you need 2 there?
2 is that they're both working.
You have to, oh, that's
This down here means 1 is working, 2 is working only. This is only machine 2 is working. This is only machine 1. Now, the reason I have to pay attention to the machines is the failure rates and repair rates differ by machine. There's lambda 1 and lambda 2, mu 1 and mu 2. This would be much simpler if they just both failed at lambda and they both repaired at mu. The thing would be simpler. Right? It would be easier. But here, 1 fails at lambda 1 and 1 is repaired at mu 1. 2 fails at lambda 2, repaired at mu 2. Yeah?
Why does the row sum have to equal 0?
Well, let's see. So one view is these are the derivatives, and if you look at the formula, the derivatives, if you think, well, this is going to be there's a bunch of answers. One answer would be that this is defined to be the derivative at 0, and when you look at this, what okay, it's a little bit confusing as to what this should be. But when you write the derivative at 0, some j. But then there's the identity matrix is going to take this away. So if you actually think about this, and you think about this, and you do the thing about what PII of 0 is not 0, but 1. This is the funny part. PII of 0 is 1, and all PIJ of 0 is 0. So actually that produces things. So if you think of ultimately that this is the derivative at 0, then think what the matrices are. You see that this should be the negative of the row sum. It's a little confusing because you don't directly define the rates. What I'm saying is when you define the Q matrix, you naturally define all the rates to the other states. And then you just put the negative of the row sum on the diagonal. And you argue that that's the right thing because why do you care what's on the diagonal? You actually want Q to be interpreted as the derivative at 0. That's the, in other words, what is Q there for? First, the off-diagonal elements are these rates. In order to say what should go on the diagonal, you have to say, well, what does this Q supposed to mean? It's supposed to be the derivative at 0. In order to be the derivative at 0, it has to be that. That's sort of, I think that may not be the best answer, but that is an answer, right? I mean, you think, oh, when I solve this, I'm going to get to the differential equation. I'm going to have this differential equation, and in order for this to be correct, this Q better be the derivative at 0. And that forces this structure. Whereas in modeling, you just directly define these off-diagonal elements as the rates. And in this case, all these rates are essentially, well, we were given this, but that translates into this and almost immediately into the Q matrix. But this is a different view than the salesman. This view is the models given to you as rates. So if you were yourself now employed and somehow you had it in your head that now is the time, project into some future place, you now have some problem, and lo and behold, you have convinced yourself that this is time to dredge up what you learned in IOR 4106, you would then sit there and think, you would then have to think, what would these rates be? What should they be? You would start to doing something about how often, what is the rate these machines break down and so forth. You might be actually seeing, over 6 months this machine broke down 30 times. So then I say, well, okay, that's so much per hour. The intensity to break down, you may be doing it in a very rough way because you don't know the local derivative. So you may be defining the rate in terms of a long-run rate. But you make a model, you somehow have to do, if you're going to do this, you may put down these rates. It's much less obvious where these rates come from, admittedly, right? Where would you get these rates? It's a little bit problematic. But if it's machine breakdowns, that's, if it was exponential, then long-term and short-term rates have to agree. Well, so let me just review the applications. This application has these machines that are working or failed, and when they're working, they break down at some rate, and when they're failed, they're being repaired at some rate, and you specify as part of the model data what these rates are. And that leads to this picture of the state diagram with all the rates, and that leads to the Q matrix. And the Q matrix then leads to solving the system by just alpha Q equals 0. So rates become, in this view, the model is the rates. So in continuous time again, continuous time, there's the rates, and you get the rates, and then you solve alpha Q equals 0. If you take a semi-Markov process view, you have the discrete time chain and these mean holding times. And you find alpha of some state, alpha j, is the weighted pi j mj over the sum of the pi k mk's. So two different representations, two different model datas, representations of the solution, and the models are equivalent. Everything will be the same. They'll be equivalent. So that and then these two problems, one is expressed directly this way, and the other is expressed directly this way. And you could simplify life and jam in your mind everything down to one way of looking at it. It's helpful, I think, to realize, if you realize what I'm saying, the point I guess I'm thinking is, if you see these two problems and think about them, they're worded so differently, it's very confusing. It's much better at a high level to recognize that there's two basic fundamental ways that you can look at these problems. Different, very strikingly different, these two problems. Once you know there are these two ways, you see it fits right away. If you think there's only one way, that you think, geez, this doesn't look right. You've got to convert one into the other before it's a little confusing. Once you know there are these two ways, the problem just hits you right between the eyes. Oh, this is that way, or this is this other way, and then it's clear. So in sort of the structure is that this view of the thing is very important to kind of see what's going on, that there's these two representations, and they each have their own story, but they're equivalent. Okay, and then, so where are we going? One of the things we're going to is, just like in discrete time Markov chains, there's special structure that makes it easier to solve these things, right? Reversibility will be there. So the problems are even faster. You could find this alpha even more quickly if you have extra special structure. So this isn't the end. This is the general view for continuous time, just like pi equals pi p is in discrete time. But you don't just do that. There's extra things you can do, extra, like the chess. There's, in fact, most of the continuous time theory is actually jammed full of many complicated systems that can be solved by reversibility. So the classic case is queuing networks, where you have a whole network of queues, and each queue is one of these, like a continuous time Markov chain, but the things are going from, not only from the system, not only are there arrivals and departures at each queue, but they're going from one queue to the other, and the state space is a big vector of how many jobs are at each of the queues and so forth. And this complicated system can have a simple solution, just like essentially for the same reason that you can quickly calculate the probability the knight's going to be in the corner after 1 billion steps or whatever. Right? The same. There's these other complex models have the same beautiful story of simplification. Okay, it's if you were doing the secret word, we've got to the word, right? Lunch. We got to lunch. Okay, that you're going to see this. This is, if it made little sense, you'll see the notes online. That hopefully that together will help.